Now the next thing we are going to start, it is finite and infinite sets. So before we start discussing the finite and infinite set, it is important to understand how the natural numbers they help us to count the things, or they can help us to determine the size of a set. And for this, let us look at the set of natural numbers. We are saying the set of natural numbers it is represented with n, and it consists of the elements 1, 2, 3, 4, 5, 6 and so on. These three dots when we are putting over here, it means so on. They will continue like this. So if we talk about the smallest natural number, the smallest natural number that we have, this is 1. And when we are talking about the largest natural number, look at this set over here. There is no largest natural number, because whatever number you will write, you will obtain another number. If you will write n is the largest number, you will write n plus 1 and you will obtain the next natural number. So we are saying that there is no largest natural number. And on number line, how we are going to represent these numbers? Why I have put dots over here? Because we are talking about this is the number 1 that we have. Then we will have 2, then we will have 3, then we will have 4, then we will have 5, and this will continue. This is how we can represent the natural numbers on a line. Then next we look at the properties over here. We are talking about the closure property. We can see that if I consider any two natural numbers and I add them, the answer I will obtain, that is a natural number. And if I am talking about any two natural numbers and I multiply them, if I multiply any two natural numbers, the answer I will obtain, that is again a natural number. So what we obtain is that the collection of natural numbers, it is closed under addition and multiplication. If we are talking about subtraction, if I subtract 2 from 3, it is not a natural number. If I divide 1 and 2, it is not a natural number. So we are saying that natural numbers, they are closed under addition and multiplication. So closed under means that if I add two natural numbers, answer is a natural number. If I multiply two natural numbers, the answer is a natural number. So these are some basic properties that I have listed over here. Then solvability we are talking about. If we have the equation of the form x plus 2 is equal to 3, and if I have the equation of the form x plus 2 is equal to 1, so we are saying the set, the answer in this case, we will have x is equal to 3 minus 2 is equal to 1, and this is a natural number. 1 belongs to set of natural number, means 1 is a natural number. And I am talking about x plus 2 is equal to 1. We have x is equal to 1 minus 2, and this does not belong to the set of natural numbers. So we are saying that set of natural numbers are not sufficient to solve this kind of equations. Now, the first application of natural numbers that comes to our mind, that is they are used for counting. So let us see that how counting works using the natural numbers. Suppose I have some jars. And I want to count that how many jars are there. These are some jars, and I want to count how many jars are there. So what I am going to do, I am going to consider a jar. I will take a jar and I will say this is 1. I will take another jar, I will say it is 2. I will take another jar, I will say it is 3. I will take another jar, I will say it is 4. Likewise, I will continue in this way. And I will assign a number to each of these jars. I will assign a different natural number starting from 1, 2, 3, 4, 5. I will go on assigning the number to these jars. Finally, when I have taken the last jar, I have assigned the number 7. And we are saying that there are 7 jars. This kind of assigning of number, this is called bijective matching. Why bijective? We are saying to every jar over here, I am assigning a natural number, different natural number. So that is why we are saying this is a bijective matching. To each jar, I have assigned a natural number. And when I have assigned the natural numbers in this way, the last number I have assigned over here, it is 7, and I am saying there are total 7 jars. So this kind of matching, it is called bijective matching, and this is how the counting works. Whenever we are counting, we are using this technique. So in terms of sets, when we are talking about these sets, we will say a set is finite if the process of counting of element it comes to an end. Otherwise, it is called infinite. Let us look at this. Suppose I am talking about a set A. It has elements 2, 3, 7 and 11. What I am going to do? I am going to take one of the elements over here. Say the element 3 I have taken. I have assigned it the first natural number 1. Take another 3 I have now taken. I have assigned this number. Take the element 2. Assign it the number 2. Take the element 7. Assign it the number 3. Take the element 11. Assign it the number 4. These are the natural numbers we are talking about. The process of counting it comes to an end. We are saying this set is finite. If the process of counting does not come to an end, we will say the set is infinite. And the number of elements that this set has, this finite set we are talking about, that is called the cardinality of the set. So in this case, we are talking about cardinality. We can write n of A, that is number of elements of A, or we can write cardinality of A in this case, that is equal to 4. This is the process of counting, it comes to an end, that is the cardinality. How many elements that set has? Cardinality is basically how many elements, the number of elements in that set, it is called the cardinality of the set. Things will be more clear to you with our next examples. First example we have, it is the set with the single elements. The sets that have only one element. They are called the singleton sets. Simple. Singleton set means set with only one element. Example is given over here. We are talking about x. What property x is satisfying? One property that x is satisfying is x is a natural number, and x square is equal to 4. If you will solve x square is equal to 4, you will write x is equal to 2 and minus 2. X is also satisfying this property. X is a natural number. Minus 2 is not a natural number. It means that in this collection, we have all the x which satisfy these two properties. From this property, what we observe that x can be 2 or minus 2. Then we impose this property over here. We are saying x should also satisfy that x is a natural number. Minus 2 is not a natural number. This element is removed. We are left with that this set it has only one element, that is 2. Now, note over here, whenever we are writing 2, this is the number 2 we are talking about. When we are writing it in brackets, in curly brackets, this is set containing number 2. How many elements are there in this set? There is only one element, and that element is the number 2. So these two things, these are different. When we are writing 2 over here, it is the number 2 we are talking about, and when we are writing these brackets over here, it is the set containing the number 2. Similarly, if I am writing the set A, it has the element 0. Observe over here, we are talking about when we are writing this. This is the number 0. When we are writing this is set containing the number 0. So how many elements this set has? It has only one element. So we are saying the cardinality of the set A, that is equal to 1. You can write n of A is equal to 1. You can use any of these two notations. So both of these sets, they are the singleton sets. Singleton set means that both of these sets, they have only the single element. Next we have is the set is given. Now we have to tell whether this set it is a finite set or not. So to tell whether it is finite, we are saying we assign the number 1 to it, we assign the number 2 to the next element, we assign the number 3, we assign the number 4, we assign the number 5, we assign the number 6. The process of counting comes to an end. This is a finite set. Number of elements in A or cardinality of A, that is equal to 6. Consider another example. We are saying we have a set B. It is all the letters in the English alphabet. A, B, C, so on up to Z. Assign the numbers 1, 2, 3, so on up to 26. The process of counting comes to an end. This is a finite set. Number of elements in the set B, that is 26, or we are saying the cardinality of B is 26. Another example. This is an interesting example now. The set of all leaves on a tree at a specific time. There is a particular tree we are talking about, and at a particular time I am talking about the number of leaves on that tree. So we can say that the number of leaves on a tree at a particular time, they may be in thousands or they may be even in millions. But at a specific time, there will be a finite value. The number of leaves that we will have, it will have a finite value. That is, if we start assigning the numbers, if we take the first leaf and I am assigning it the number 1, I am taking the second leaf, I am assigning it the number 2, and I continue like this, assigning the numbers to all the leaves. It may take some time to count those, but clearly we will have a final number over here. We will have some number that will be assigned to the last leaf. What we mean to say is that the process of counting, it comes to an end. It may take a lot of time to count those leaves, but the process of counting will come to an end. It means that the set of all leaves on a tree, it is a finite set. Now the cardinality may be in thousand, it may be in millions, or it may be any particular number, it may be very large, it may be large, but the process of counting will come to an end. Let's consider another interesting example. We are seeing the set of all persons on the earth at a specific time. So when we are talking about the set of all persons on the earth, so at a particular moment of time, we are saying that every person that we will have, it will be a distinct person. That will be a distinct person, and we can identify each of these persons. It means the first thing we will get, it is distinct, and we can identify each person of every person on the earth. So it means that this set we are talking about, it is well defined. It is well defined. So it means that every person is distinct, every person is identifiable. Suppose I am talking about at this particular moment, there will be some limited population. I am talking about a particular instant of time. Someone might be dying, someone might be getting the birth, but at a particular moment of time, there will be a specific number. Say that number is 8 billion. At this moment of time, we are saying, so there are 8 billion persons on the earth. It means that if I will start assigning the numbers 1, 2, 3, so on, to the last person of the earth, I will assign the number 8 billion. I will assign the number 8 billion. It means the process of counting the number of persons, it comes to an end. The process of counting the number of persons, it comes to an end. So we are saying that the set of all persons on earth at a specific moment of time, it is a finite set. This set is also a finite set. Let us consider another example. The set of all positive integral multiples of 5. Positive integral multiples of 5, 10, 15, 20, 25, 40. Start assigning the numbers 1, 2, 3, 4, 5, continuous. The process of counting does not come to end. When we are counting the number of persons on the earth, we are saying the last number may be 8 billion, it may be 9 billion, it may be any particular number. But the process of counting will come to an end. That is why that set it is a finite set. In this case, the process of counting will never come to an end. We can always obtain. Suppose I am saying some number n is there, I will always obtain another number n plus 5. That will be the next positive integral multiple of 5. So because the process of counting it doesn't come to an end, we are saying this set it is an infinite set. Another example. The set of all points, the set of all points on a line segment. Suppose I am talking about this is a line segment that we have. We are not talking about infinite, we are talking about a line segment. These are the endpoints. I am talking about the set of all points. Suppose we have marked these points. We are saying 1, 2, 3, 4, 5 and 6 points. Between 3 and 4, we can mark another point. Say it is 7th point. Between 3 and 7, we can mark another point. Say we are saying this is the 8th point. Between 3 and 8, we can mark another point. Say it is the 9th point. We have no smallest unit over here. We have no smallest unit over here. That is, we can continue obtaining more and more points in between over here. So the process of counting the number of points, it will not come to an end because there is no smallest unit over here. So we are saying that this set is an infinite set. Let's consider another example. The set of all straight lines parallel to x axis. These are the axes we are considering. This is the x axis, this is the y axis. I plot a line over here. This is the number 1 we have. I plot a line over here. Equation of this line, that is y is equal to 1. I plot another line over here. Equation of this line, that is y is equal to 2. I plot another line over here. Y is equal to minus 1. In general, the equation of line we have, that is y is equal to c, and c is a real number. Look at this number c. There is no largest or smallest value. There is no largest or smallest value, or you can say there is no upper or lower bound on this c over here. So it means that we will obtain the process of counting these lines. The process of counting these lines, it will never come to an end. So this set is an infinite set. So this set, it is an infinite set. Next, the set of all circles passing through a given point. We are talking about the set of all circles passing through a given point. Again, consider the axis over here. The given point, suppose we are talking about this is the point 0. We want to find all the circles passing through this point. I draw a circle over here. The center of this circle, say it is 1. The radius of this circle, it is 1. I shift the center of this circle. This is the point 2 now. I shift this, I draw another circle whose center is at 2 and radius is 2. The center of this new circle, center is 2, radius is 2. Center is 1, radius is 1. I draw another circle, say this is the point, now this will be the point 4. Suppose I draw another circle whose center is 4 and radius is 4. Center is 4, radius is 4. Similarly, on this side, I will obtain one circle, then another circle, then another circle. So, what basically we are doing? We are saying, look at these centers, look at these radius. We can take infinite values for the centers, we can take infinite values for the radius. It means that the number of circles that we will obtain over here, they are infinite. That is, we cannot count. We avoid using the term count over here. We just say that the process of counting, it never comes to an end. So that is why we are saying the set of circles passing through a given point, it is an infinite set. Now, we have seen what a finite set is, what an infinite set is, what a singleton set is. Another important kind of set that we have is set with no elements. So, to start this, we start with the set of whole numbers. When we are talking about whole numbers, natural numbers we were saying 1, 2, 3, 4, 5 and so on. These are the set of natural numbers. When we include this number 0 over here, we are saying we have the set of whole numbers. So why 0 was introduced? We were saying natural numbers, they are used for counting 1, 2, 3, 4. When there is nothing, number 0 is there. We are saying that 0 means there is nothing over there, there is no object over there. So when we are saying empty set, we are saying set that has no elements. That is called an empty set. Empty set, they are also known as null set or a void set. And we can represent the empty set with empty bracket, there is no element over there. We have this empty bracket, there is no element over there. or we are going to represent it with the symbol phi. So this is the representation of empty set. Either we can represent it in this form or we can represent with the symbol phi. And if a set has some element, we will say it is a non-empty set. We have two terms over here. One is empty set, one is non-empty set. Element is set having no element, empty set, can be represented in any of using any of these. If this is written somewhere, it means we are talking about empty set. Empty brackets are there, empty set. And if a set has some element, it has number 0 in it, that set we are saying it is a non-empty set. So let us look at some examples. The first example we have over here. We are saying the first one, the set of all x. X is a natural number and x is between 2 and 3. So is there any natural number strictly between 2 and 3? No. So clearly this set, it has no elements. There is no element which satisfies both these properties. The element should be a natural number and it should be between 2 and 3. Not possible, it is an empty set. You can use any of these representations. So we are saying this is an empty set. We are saying x is a real number and x square is equal to minus 1. Can there be a real number whose square is minus 1? Not possible. Because we know that the square of any real number, that is always positive. There is no real number whose square is negative. So clearly this set is also an empty set. X is a rational number and x square is equal to minus 2. If we will solve this equation, we will obtain x is equal to plus minus square root 2. Square root 2 we know it is irrational. So we are saying there is no x which satisfies x square is equal to minus 2 and x is a rational number. So this set is also an example of an empty set. There is no element over there. Next, set D is there. X such that x is not equal to x. Can there be any number or anything which is not equal to itself? We are restricted to numbers over here, particularly the real numbers over here. So we are saying that every real number is equal to itself. It means there is no real number which is not equal to itself. So clearly this set is also an empty set. So these are some examples related to empty set. Empty set means the set having no elements. You can represent them with the empty brackets or symbol phi. So there is a remark over here. First is the set this an empty set? No, because it has the element 1 over it. It has the element 1 over it. It has one element. It is a singleton set. It is not an empty set. Is the set 0 an empty set? So there is an element 0 over here. So let us try to understand this using the circles. That the representation of sets we are talking about. I am talking about a set this, I am talking about a set this, and I am talking about a set this. What this is representing? This is a set with the element 1. Clearly it is not an empty set. This is the set with element number 0. In this set, there is a number, there is an element that is number 0. How many elements are there in this set? There is, in this set, number, say this is the set A, this is the set B, and this is the set C. So number of elements in B is 1. Number of elements in set C is 1. That number itself it is 0. And number of elements in the set A, that is 0. So this is the empty set. This is the empty set. But these two sets, they have one element. So these two sets are not the empty sets. Next, is the set of intelligent students in a class, the set of intelligent students in a class, a null set? So when we are talking about this term intelligent, this is a subjective term. So when we are talking about the set of intelligent students, we are saying that this collection, it is not a well defined collection. This is not a well defined collection. So it is not a set. So there is no question whether it is empty set or it is finite set or it is infinite set. For everything like this, if we are talking about it is an empty set, it is singleton set, first of all it should be set. But when we are talking about this collection, we are saying it is not a set. So we are having two different things now. One is not a set, and another thing that we have is empty set. So for a set to be empty set, it should be a set. First of all, it should be a set, then we will say it is an empty set. In this case, we are saying it is not a set. So we are saying the set of intelligent students in a class is a null set. We are not talking about this condition. We will say that this is not a set, so we will not say it is a null set. So these are two different things. When we are saying empty set and we are saying not a set, so these are two different things or two different concepts. The next term we have is the equal and the equivalent sets. So two finite sets, note over here we are talking about finite sets. They are said to be equivalent if their cardinalities they are same. That is, number of elements in A that is equal to number of elements in B. Or we are saying cardinality of A is equal to cardinality of B. Number of elements. We are not talking about what elements are there. We are just talking about number of elements are same. We will say they are equivalent. And two non-empty sets. We are not talking about finite now or infinite now. They may be finite, they may be infinite. Two non-empty sets A and B are said to be equal if they have exactly same elements. When we are talking about equal, we are concerned about the elements of the set, that what elements are there. When we are talking about equivalent, we are talking about the number of elements of that set. So this thing will be more clear to you when we are going to discuss this theorem. It says equal sets are always equivalent, but equivalent sets, they need not be equal. So in the first part, we are going to talk about equal sets are always equivalent. Definition of equal set that we have is they have exactly same elements. I am not talking about the formal proof. This is not the formal proof. We are just trying to understand what this theorem is saying. We are saying we have two sets A and B. We are saying that these are equal. It means they have exactly same elements. If they have exactly same elements, this means this is the symbol implies that number of elements in the set A that is equal to number of elements in the set B. We are saying two sets are equal. They have exactly same elements. If 1, 2, 3 is element of A, 1, 2, 3 is the element of B. It means number of element in A, number of element of B equal. It means that these two sets they are equivalent. These two sets they are equivalent sets. The first part. Consider a set 1, 2, 3. Consider a set A, B, C. Number of elements, so this is X, this is Y. Number of elements in X is 3. Number of elements in Y is 3. Number of elements in both these sets they are equal. these two sets, they are equivalent. Number of elements, they are equal, they are equivalent. Look at the element, 1 over here, A over here. Elements are not same. It means these two sets, they are not equal. What we obtain? If the sets are equal, they are always equal because the number of elements will be equal. But it is not necessary that if the number of elements they are equal, then the sets they are same. A formal proof of equality or equivalent or this theorem we will look in our next lectures. So right now you just try to understand this thing, that when we are talking about equal, they have exactly same elements. When we are talking about equivalent, they have same number of elements. Things will be more clear to you with our next example. So we are saying, let we have two sets. One is the set of letters of the word follow, and another is the set of letters of the word was. We have F, O, L, L, O, W, W, O, L, F. We have these two sets. O is repeated, we leave this O. L is repeated, we leave this L. When I have to write the set corresponding to this, I will have F, L, O, W. Say this is the set A. We have the set B, it has elements W, O, L and F. Repetition of elements and order of element doesn't change the set. W is there, W is there, same element. O is there, O is there, same element. L is there, L is there, same element. F is there and F is there, same element. Both the sets have exactly same elements, so both these sets they are equal. They have exactly same elements, so both these sets they are equal sets. Another example. Consider the set having an element 0 and another set is an empty set. One set is this and one set is this, or we can say this is this. Element of this set, it is 0. There is no element in this set. Number of elements in this set, it is 1. There is one element. If I am writing this is the set A, this is the set B. Number of elements in the set B, it is 0. So both these sets they are not equivalent because number of elements in A is not equal to number of elements in B. So these two sets they are not equivalent sets. If they are not equivalent, then they cannot be equal, because the first condition for equal is they should be equal. Moreover, you can see over here, the element over here is 0, there is no element over here, so clearly these two sets they are not equal sets. They are not equivalent sets. So this is all we have right now. So next we have some problems that you can try at your own to check your understanding related to this lecture. So these are some problems that are present in your lecture notes. These are already provided to you. These problems, these are already provided to you. These are based upon this particular lecture. So, you must try these and check your answers, and if you have any doubt, you can ask me in the doubt session.